Welcome to this talk on post-quantum cryptography and the way forward. My name is Mike Agrenius Kushner. I'm a product architect at Keyfactor. So some basic credentials. I've been working with public key infrastructure since 2010, primarily with an open source product by name of EGBCA. Had several roles, but as said, currently working as an architect. Now, we are here, September, in the year of our Lord 2024. About 1 month ago, NIST released the final post-quantum algorithms, the result of 8 years of hard work. Fun fact, these are no longer known by their old names of dilithium, Sphinx, and Kyber. The official names now are MLDSA, SLHDSA, and MLChem, because they have changed significantly since they were first submitted. Now, how are they different? They are much worse. They have bigger keys, they have bigger signatures, they are slower, and they introduce the concept of chems. So I think most of those points are pretty obvious, but what is a chem? A chem is a key encapsulation mechanism. So while RSA can basically, if you're sending over a symmetric key, RSA can do it organically by encrypting it. With EC, you can use a Diffie-Hellman key exchange. The new algorithms aren't capable of this, so they need a separate mechanism, which works a bit like Diffie-Hellman, but while Diffie-Hellman is what's called a NIKE, or a non-interactive key exchange, where you basically just send something over and both sides can figure out the shared key on their own. In a chem, you need a bit of back and forth. So what is this going to mean to us and the entire ecosystem? Well, most of us aren't going to notice the slower speeds, but high throughput and constrained environments are going to notice it. We're going to have a period of upgrades, and upgrades are going to mean some failures, as certain servers have cutoff points and all clients won't have caught up. And we are all going to be doing a lot of upgrading. But for those of you following the science, you will know that there are maybe, I think, about 2 Nobel Prizes in physics between now and having a practical quantum computer. So why am I standing here and fear-mongering? Well, 3 reasons. 1, there's a deadline. 2, there is the concept of forward secrecy. And lastly, the concept of crypto agility. So first of all, the timeline. So the NSA, now in August, released the new cryptographic recommendations, and they specify that all code signing must be done with post-quantum algorithms by 2030, followed by all encryption and all signing in general being done with post-quantum algorithms by 2033. Now, code signing certificates, they can have lifetimes up to like 10 years. And yeah, count off the number of years between now and 2030. Then there's the concept of forward secrecy. Now, how important forward secrecy is entirely up to your use case. Some cases it's going to be 5 minutes, 10 years, 20 years. But whatever the case, whatever you're transmitting right now has to remain unbroken for n number of years. Likewise, what you sign now, think code signing, has to remain inviolate for n number of years. And there are plenty of actors who are harvesting this data right now in the hopes of being able to either decrypt it or falsely sign something in 5, 10, 15, 20 years' time. Crypto agility is a fun buzzword which gets thrown around. I define it as the ability to migrate your ecosystem from one cipher algorithm to another. Now, this sounds fairly simple. I mean, it's just like, okay, we'll just change this algorithm to that. But I have a really good example of why it's way easier than it sounds. So let's take SHA-1. SHA-1, first vulnerabilities were found back in 2005. That's back, I was still in university then. But it was declared deprecated by the NSA in 2011. Now the browsers, who are certainly no slouches when it comes to security, I would say they're at the forefront. They were unable to disallow SHA-1 until 2017, Why? Simply because the ecosystem didn't have time to catch up. If they had gone in, say, 2014 and dislodged SHA-1, a large part of the web would have been unable to use TLS. So upgrading on the certification side, that's the easy part. Getting your entire ecosystem in line is the hard part. Imagine, take Let's Encrypt, the largest CA. They have, last time I checked, about 240 million active TLS certs. That means 200 million something active cert bots or other Acme clients, which all have to be upgraded to be able to speak post-quantum. So, you know, play in your heads. How long do you think it would take to get up to 99% upgraded? So this is going to imply a period where we're going to have to handle post-quantum keys and the legacy keys at the same time as the ecosystem is slowly upgrading. Now to solve this, the IETF have been extremely busy and currently have not one but four possible solutions in draft. These are hybrids, chameleons, composites, and Merkle tree certificates. Hybrid is probably the simplest solution. Simply adds a number of non-critical extensions to X509, also known as Catalyst. These extensions being non-critical means it's perfectly backwards compatible and is, of the four, the only one which has actually been put into practice right now. Chameleons is kind of a step beyond hybrid. They involve the issuance of two certificates, a base certificate and a delta certificate, and they're linked by a descriptor extension in the base. And if you have the base and the descriptor, you can simply derive the delta. So at whatever point you decide on a cutoff point, all your clients can simply take the base certificate that they already have downloaded and derive the delta out. Again, the extension is non-critical, so chameleons are also perfectly backwards compatible. And a nice feature with chameleons is that these certificates can have different validities. Above all, they can be revoked separately. Then we have the first step away from backwards compatibility, composites. So composites essentially combine the signatures of several algorithms into one big amalgamation. This takes a pretty big step away from X509, so composites are not backwards compatible. One of the features of composites is that all these algorithms are new. I'm sure there are exploits which will be found in 5 or 10 years, even though NIST have been working extremely hard. So composites kind of safes up by using a legacy algorithm, because they're still safe so far, and adds several other algorithms and makes one big blob out of that. Lastly, there is a draft being developed by Google and Cloudflare, which is specifically designed for the TLS use case and takes into account the large signature sizes. So Merkle tree simply takes the signature from the certificate, strips it out, leaving you with a certificate which is less than a kilobyte large, and puts it in a delegated or in several delegated ledgers, much like the certificate transparency system, which is used today. So you get a really tiny certificate. The only problem is that writing to these ledgers can take up to an hour, which is maybe not optimal in many use cases. Also, if you happen to be in a garage and you don't have any connectivity, you're dead out of luck. So of these four, which is going to be the path forward for this crypto agile period until the cutoff points? Good question. I think I know where I have my money, but I'm not going to say that in front of a full audience. But I think we'll simply have to see. So, what should your migration plan be? And this is really if you are working with cryptographic keys in any way, whether you are issuing certificates, using certificates, or both signing things. Now, how much of a hurry you need to be kind of depends on who you are. Government agencies, especially those in the intelligence community, they are already well ahead. But of course, they're going to start putting demands on regulated industries, such as finance, telecom, so forth. So if you are working with or serving in one of those industries, you should probably be in a hurry. But of course, by the cutoff points, everybody's going to be into this. So our recommendations of kind of what you should have been doing already before you got here. Well, remember what I said about crypto agility. 2030 is not far away. I would recommend making an inventory of your use cases and your risk exposure, and the inventory of algorithms and keys you use today, and start making plans for when and how you're going to make the algorithmic changeover, hopefully in good time before the deadlines. And above all, design with crypto agility in mind. Anybody here who's worked with third-party clients, basically anybody who's not Microsoft, will know it's incredibly hard to get people to upgrade, especially if everything's working fine. In terms of certificates, people usually, the only way of getting somebody to renew a certificate is basically by waiting for it to expire. That's the first time they ask what's up. So keep the time frame in mind when planning your upgrade. Now, our recommendations for what to do tomorrow when you get home. Well, start looking at what you can do today. OpenSSH has had post-quantum key exchanges since version 9. So yeah, no reason not to use that now. If you're using soft keys, then it's a good chance to upgrade your or create post-quantum trust roots. If you're using HSMs, it's yeah, please badger your vendors to start supporting post-quantum keys. They are late on the ball. If you're doing any type of code signing, again, code signing certificates have long lifetimes. I mean, imagine an IoT device. From the time it comes out of the factory to the time where it comes out of the box and connects, it could be 5 years, and a lot can happen between them. And if that thing wakes up and the post-quantum apocalypse has happened, it's bricked. So, and as soon as you can, begin issuing post-quantum certificates of whatever variant fits your use case. And also start badgering your clients to upgrade. If you'd like to read more, Keyfactor has created a post-quantum lab, which can be found at the above URL or at the top QR code, with a lot of interesting reading and stuff we've compiled. Also, the IETF has a really good document titled Post-Quantum Cryptography for Engineers, which can be found at the bottom link. So, my name is Agrenius Kushner, and thank you for your time.